Hi everybody, this is Mr. Bowman again. We are almost finished with Chapter 3, but there's a couple really important things we have to talk about. And today we're going to talk about R squared. That's right, the correlation coefficient squared, and what it means and how to find it. And we're also going to talk about S. So, to start out this activity, we are looking at body weights in pounds versus backpack weight of a small group of individuals. So what I would like you to do is I would like you to pause the video, find the least squares regression line for predicting backpack weight based on body weight. So body weight is the explanatory variable and backpack weight is the response variable. So what you should have found is that predicted backpack weight is approximately 0.09 times body weight plus 16.26. You should have also found that the corresponding residual plot shows very little pattern and the scatter plot is linear, so it's appropriate to fit a line to this data. Well, what we would like to do is we would like to be able to quantify how well our least squares regression line predicts body weight. And to do this, we are going to start out by finding something called S, or the standard deviation of the residuals. So if you take a look at this formula in depth, it actually tells you a lot about what S tells us. So the way this formula works is we take each of the residuals. Remember, residuals could be positive or negative. We square them, we sum them all up, and then we divide by something related to the sample size, which in this case is actually the sample size minus 2, and there's an explanation for that. But basically, think about squaring all the residuals and adding them, because if you don't, they're actually going to add up to 0 all the time with the least squares regression line. Square all the residuals, add them all up, divide by something related to the sample size, and then finally take the square root of that to undo the fact that you squared them. That is the residuals. So you get a standard deviation, and it's the standard deviation of the residuals. And for this particular example, it turns out that the standard deviation of the residuals is 2.27. So what does that actually tell us? Well, here's what it tells us. It tells us that the average deviation of the actual backpack weight from the predicted backpack weight for a person of that weight, using this least squares regression line, is about 2.27 pounds. Now, you got to think about that in context. In context, our backpack weights range from about 24 pounds all the way up to 35 pounds. So we have an average error of, I don't know, somewhere in the neighborhood of 10% or slightly more. Depends on how you feel about this, but as far as I'm concerned, that seems like a pretty good prediction, particularly based on such a small sample size. So again, the way we interpret S in context after we find it, which we'll talk about how to find that later on, is S represents the average error in the predicted response variable based on this least squares regression line. So in this case, it's the average error in the predicted backpack weight, and in this case, it's 2.27 pounds. The next thing we want to talk about, another measure of how well the line of best fit fits the data, or how well our line of best fit makes predictions for us, is R squared, also called the coefficient of determination. And it is really the linear correlation coefficient squared, but you have to know that, and you also have to know it's called the coefficient of determination. So we're going to work through how to interpret that. And this is kind of challenging, so please pay close attention, pause the video when you need to. So to deal with that, the first thing we're going to do is we're going to find the average value of the response variable, so the average backpack weight. So pause the video, find the average backpack weight from our sample. It turns out that the average backpack weight for our sample is 28.625 pounds. Well, what you see here is a scatter plot of the actual data, body weights versus backpack weights, the least squares regression line drawn in green, and Y bar, the average backpack weight, a horizontal line drawn in as well. So what R squared tells you is the proportion of the variation in the response variable, backpack weight in pounds in this case, that can be predicted by the least squares regression line. And that number theoretically could range from 0% to 100%. And what I want to do is I want to illustrate that concept with this graph, and then I want to go through the calculation of it. So let's say we pick this point right here. I'm going to highlight it in yellow. And we could say that there's this much total deviation from the mean for that point. What we'd like to be able to say is how much of that total deviation can be predicted by the line of best fit. Well, for this one point, this much of the deviation can be predicted by the line of best fit. This much of the deviation cannot. So for this particular point, if I had to estimate, I would say that about, 40% of the deviation from the average backpack weight can be predicted by the line of best fit, and the other 60% cannot. So what we do is we go and we take into consideration how much of that deviation from the average Y value for every single point can be predicted by the line of best fit, and we sum all those values up, and then we have an overall percentage of variation in the response variable that can be predicted by the line of best fit. And when we say percentage or proportion of variation, we're talking about from the average Y value, whatever that is. So as is typical, if we were simply to add up all the deviations from the average Y value, you will see some of them are positive and some of them are negative. And it turns out that if we sum them all up, they would all add up to 0, which is always going to be the case, just like it did for the standard deviation of X values. So, like we typically do, what we're going to do is we're going to square all those deviations, and those deviations squared are going to be represented geometrically by the area of a bunch of squares. And then we're going to sum those up, and then we're going to do something related to the sample size, and so on and so forth. All right, so if you take a look at the diagram on the next page, again we have Y bar drawn in and all of the deviations from the mean squared, which are represented by the areas of all these squares. And if you were to go through and find all those deviations squared, the actual Y value minus the average Y value, and then square them, what you would find, and then add them up, what you would find is that for this particular example, they are going to sum up to what we call the sum of the squares of the total deviations, which is 83.87. In this next diagram, what we're doing is we are finding the portion of the total deviation that cannot be predicted by the line of best fit. And just for illustration purposes, I'm going to draw in the Y bar line, which was about right there, Y bar. And so what we found a minute ago was the actual deviation portion that can be predicted by the line of best fit, so the area of this blue square, let's say, that I'm shading. What we're now going to find is we're going to find the area of all these green squares, which is the portion of the deviation from Y bar that cannot be predicted by the line of best fit. And to find that, what we do is we find the residuals. We take the y value, actual y value, minus the predicted y value, and we square those, and then we add all of those up. And in this particular example, when we do that, we get what is called the sum of the squared errors, which turns out to be 30.9. So now in this next diagram on the next page, things start getting pretty complicated if you're looking at the diagram, but we've broken this down into two parts. We've broken it down into the sum of the squared total deviations from the mean and the sum of the squared errors, or the part of the deviation from the mean that cannot be predicted by the line of best fit. So what we're going to do is we're going to find the ratio of SSE, sum of the squared errors, over the sum of the squared totals. And what that tells us is the proportion of the total variation from the mean that cannot be predicted by the line of best fit. And for us, that number turns out to be, you'll recognize these numbers, the 30.9 divided by the 83.87, or 36.84. So what we're saying is that 36.84% of the total deviation from the mean cannot be predicted by the least squares regression line. Okay, so if you're telling me, or I'm telling you, that 36.84% of the total deviation from the mean backpack weight cannot be predicted from the least squares regression line, that means the rest of it can. So to find what percentage of the deviation from the mean backpack weight that can be predicted by the least squares regression line, we take 1 minus our SSE over SST, and we get that proportion, which is about 63%. That is the coefficient of determination. So the coefficient of determination, designated as R squared, can be calculated using this formula right here. R squared is equal to 1 minus SSE over SST, where SSE is the sum of the squared deviations from the line of best fit, also known as the sum of the squared residuals, and SST is the sum of the squared deviations from the average y value, also known as sum of the squared totals. So you will have to commit that formula to memory. That formula is not on the formula sheet. There's one other way that you can find R squared, and that would be by taking the correlation coefficient and squaring it. So what I'd like to do now is I'd like to finish up by taking a look at some examples in detail. So suppose you have a data set where all the points fall on the least squares regression line. In that case, what is the value of the sum of the squared errors, or sum of the squared deviations from the line of best fit? Well, if all the points fall exactly on the line of best fit, we know that R is going to be either -1 or +1, and we also know that there are no errors, so SSE is 0, so our line of best fit is perfect at predicting variations in the response variable, so R squared would be 1. Question B, do you think it's possible for SSE to be greater than SST? Well, SST are the total deviations from the average value, and either some of that or none of that can be predicted by the least squares regression line. If none of it can be predicted by the least squares regression line, then SSE would have to be the same as SST. So SSE could never be bigger than SST. What do you think is the largest possible value for SSE? Well, in that case, SSE could be equal to SST, in which case we're basically saying our least squares regression line predicts none of the variation in the response variable from the mean value, or R squared is 0. That would happen if the correlation coefficient is 0, which means there is no correlation. It's just a random scattering of points. So one of the things that students often struggle with is interpreting R squared. And interpreting R squared, though we would love for you to have a very solid understanding of this, it's particularly important, sometimes you are simply asked the question to interpret R squared. And interpretations of R squared go like this. So R squared is the proportion or the percentage of the total sample variation from the mean of the response variable that is explained or accounted for by the least squares regression line. You don't have to say it in that complicated of a way. So in the backpack context, we could say something like this. 63.16% of the variation in backpack weight from the mean backpack weight can be predicted or explained by or accounted for by the least squares regression line. That would get you full credit if you're asked to interpret R squared. Occasionally, you're given a question where you're told what R squared is, often asked to interpret it in context, and then you would be asked to find the value of R. And a common mistake is for students to take the square root of R, which is fine, make sure you convert it to a decimal first, and give an answer. The problem is R can be negative, so if you use the square root function on your calculator, or you simply take the square root, you have to pay attention to whether or not the association is positive or negative to begin with. And then finally, you should go back with this particular example and verify that R squared is actually the correlation coefficient squared. And we're going to finish this activity with some important information about what we talked about. So like we've been doing a lot of in this chapter, at the end of the activities, there are some really important conclusions here. And I'm not sure why they're numbered strangely, so pay no attention to that. But take some time, read these conclusions, and if there is anything here that you have questions about, make sure you ask your teacher.